Hi class, this video is going to cover again the basic concepts of a heating and cooling curve, heating or cooling curve. So we're going to start with ice at negative 10 degrees Celsius and warm this through 120 degrees Celsius. So we'll need to begin thinking about the different steps that are going to take place in our heating curve. So we're starting at minus 10 and we're going to warm that ice until it starts to melt. So 0 degrees is the melting point. So melting begins here. And this is going to melt. Remember, we're at constant temperature. And once the melting is completed, we can start to warm water to 100 degrees Celsius. And at that point, boiling begins. And from here, we have constant temperature until it is completely vaporized. And at this point, we begin to warm that steam until we reach the final temperature of 120 degrees. Okay? And so what we're going to look at in the next few slides is how to quantify the amount of heat is required to warm the ice, how much heat is required to completely vaporize, melt the ice, how much heat is required to warm the water to the boiling point, how much heat is required to vaporize the water, and then how much heat is required to warm that steam. So there's technically 5 segments that I need to calculate of this heating curve. And so we'll walk through those 5 different steps here in the next few minutes. So we will need to know a few things. We need to first understand that there are the 2 basic things that can happen when we add heat. We can have warming, and during warming we know that Q is proportional to the temperature, and we can solve for Q using C S if we're looking at mass with mass times delta T, or we can use a Cm if we're dealing with moles times delta T. And the second is during a phase change. And here Q is equal to the number of moles times delta H of whatever process is happening. This is delta H of fusion, delta H of freezing, any of those 6 options that we have. So if we're considering the first step, we're warming from minus 10 degrees Celsius, we're talking about ice at minus 10 to the melting point, 0 degrees Celsius. So this is warming. So we'll deal with the first option here. And what's missing is some other information. We're going to talk about 1 mole of ice. Okay, and so this is what we're going to be working with this entire time. 1 mole of ice from 10 degrees Celsius to steam at 120 degrees Celsius. So we start solving. Q1 is equal to, since we're dealing with moles, we'll deal with the molar heat capacity, 37.6 joules per mole Kelvin. And remember that Kelvin and degrees Celsius can be interchanged here because 1 degree Celsius is equivalent to 1 Kelvin and in terms of the change of temperature. And so I'm dealing with 1 mole here, and then my change in temperature, delta T, is equal to TF minus T initial. So my final temperature is 0 degrees minus my initial temperature, which is 10 degrees Celsius. And so overall, my change is positive 10 degrees. So we check our units cancel out, and I'm left with 376 joules. And if we express this in kilojoules, which is a lot of times what we will find to be easiest, because we'll see in a second, some of our other answers end up being in kilojoules. This is 0.376 kilojoules. And that's how much energy it takes to warm ice from negative 10 to 0 degrees Celsius. Now if we look at segment number 2, we have a constant temperature during that phase change, that fusion state change of melting. So we're talking about melting here, and so we'll be having the phase change, and we'll use Q is equal to N times delta H of fusion. And these values are not given here, but they can be looked up and would be given for you on an exam. The delta H fusion for water is 6.02. The units here are kilojoules per mole. So when we want to melt 1 mole of ice, it's going to require 6.02 kilojoules. And so that's how much heat would require to specifically melt the ice. And we would end up with water at 0 degrees Celsius at that point. So moving forward in our calculations, we're on to step 3 now of our heating curve. And remember, step 3 now is we're taking water from, liquid water, from 0 degrees Celsius to 100 degrees Celsius, the boiling point. And so this is a warming phase again. And so Q is going to equal Cm times N delta T. And the heat capacity now for liquid water in moles is 75.2 joules per mole Kelvin. And we're talking about 1 mole still. We haven't changed the quantity. And my delta T is my final temperature minus my initial temperature, so it's 100 degrees Celsius. We check our units all cancel out here, and we get 7,520 joules, or 7.520 kilojoules required to warm that water from 0 degrees to 100 degrees Celsius. And our 4th step, remember, will be to vaporize that or boil the water. So we're going from that water at 100 degrees Celsius to steam at 100 degrees Celsius. So there's a constant temperature, and we'll have Q is equal to N delta H vaporization. And delta H vaporization for water is 40.67 kilojoules per mole. So 1 mole of water vaporizing would require 40.67 kilojoules of energy. So we are almost there. The last step is to calculate the energy of warming that steam. So we're warming steam from 100 degrees Celsius to 120 degrees Celsius. Q is going to be equal to Cm times N times delta T. So 33.1 joules per mole Kelvin. We have to remember to use the correct C, the heat capacity, for the right phase, because there is a change depending on what phase we're in. We have 1 mole of substance, and my change in temperature, delta T, is equal to T final minus T initial, so it's 20 degrees Celsius. And I keep forgetting to change this Kelvin to Celsius, but again, Celsius and Kelvin here are the same because the delta T in degrees Celsius equals delta T in Kelvin, and that's why we can keep interchanging those when we need to. So the heat here is 662 joules, and this would translate to 0.662 kilojoules of energy. And the final thing, now that we know the energy required for each segment of my heating curve, we know that the Q total here, the total heat to go from -10 to 120 degrees Celsius, is going to be equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. So if we go back and get all the numbers, which I have written down, and this is why we converted all to kilojoules. You could have converted to joules, but depending on the magnitude of the numbers, kilojoules is oftentimes a little bit easier. We started with 0.376 to warm that ice. Then we have 6.02 kilojoules to melt that ice. Then to warm the liquid water, we were looking at needing, where is it here on my paper? Oh, I see. 7.520 kilojoules, and to vaporize the water, 40.67 kilojoules, and running out of room, to warm that steam, 0.662 kilojoules. So this all totals 55.25 kilojoules of energy are required to warm solid ice at negative 10 degrees Celsius initially to steam at 120 degrees Celsius. So to conclude, we can go back to our curve and actually put the numbers on the x-axis, right? So this is going to be 0.376, and then when we add that to the heat required to melt, it is 6.396. Adding on to that the heat of warming gives us 13.92, and the most heat is required here to vaporize, and the reason for that is because there is a much larger difference going from a liquid to a gas in terms of the energy required to break those intermolecular forces compared to solid to liquid. Those phases are much closer in their likeness. And then we end here at 55.25 kilojoules. Okay, so I hope that kind of makes clear how we calculate the energy required to warm and or undergo phase changes for each segment of my heating curve. Thanks for tuning in.